Hi everyone. In the next few minutes, I would like to present the main contributions and findings of our submitted paper to MDPI Electronics Journal. Our paper entitled Quality of Service Aware Power Optimized Path Selection for Data Center Network. My name is Mohammed. I am a PhD candidate at University of Debrecen, and at the same time I am staff member of the Computer Science Department at the University of Kufa. Okay, first of all, let me give you a small introduction about the motivation of our study. In the last few years, especially due to the COVID-19 pandemic, many services have moved online. And because the data center networks are the backbone for many of these services, this has led to an increasing in data creation and copying in data center network. And as a result, the power consumption of data center network has increased. As you can see in this figure, data volume over the years from 2010 to 2025, it's estimated that by the end of 2025, the data will reach up to approximately 180 zettabyte. Of course, such increasing in data is accompanied by an increasing in power consumption in data center network. This has motivated many of researchers around the world to find different solutions for this problem. Okay, based on the literature, there are two methods to optimize the power consumption in data center network. The first one, traffic consolidation or flow consolidation, and the second one, traffic scheduling. Each method has its advantage and disadvantage. In the current study, we adopted the traffic consolidation method. However, this method could negatively affect real-time traffic application protocols, as we will explain in the next few slides. Therefore, the contribution of this paper extends our previous work where we proposed full prefer link first algorithm. This algorithm consists of three components: link utility, link cost, full shortest path. By combining the monitoring model with these components, we can achieve energy efficient path as our output from this algorithm. Okay, right now let's go ahead and describe the problem statement of our contribution. In the consolidation technique, we consolidate or aggregate the traffic from different applications in a few number of the links and paths. This can lead to most of them picking together, especially if the correlation between these flows very high. Result in high delay that affect the quality of the time-sensitive flows. This happened because it's hard to predict the bandwidth demand in advance for each flow in data center network. Therefore, this study aims to mitigate such side effect by proposed a new framework named QoS. Okay, here the proposed framework, it consists from three layers: application layer, control plane layer, and data plane layer. All these proposed model run on top of the SDN controller and SDN controller connected to the Mininet emulator using OpenFlow sequencer, where we emulated our data center network topology, and we use DITG to replicate the statistic properties of non-real-time traffic application, and VLC player to generate real-time video streaming, as we will see shortly in the practical example. Okay, right now let us see how these models in the application layer interoperate and interact with each other. Actually, we describe this model very well in our paper. However, briefly we will describe them here. First of all, we will feed the classifier with all the new flow events. The classifier check the type of the flow using the first bucket in only. That means it is a lightweight classifier. The output is the flow class. Then the monitoring module periodically measure the delay time of real-time flows. If the delay exceeds the threshold, in our case it was 75 milliseconds, the monitoring module triggers a delay event. This event prompting our suggested or proposed algorithm QoS to evaluate all available and active installed paths to find suitable alternatives path that conserve power while meeting real-time traffic requirement. The output consists of three solutions: best case, mid-range case, and worst case. In the first one, we will keep the same level while improving the quality of the service of real-time flows. However, in the second and the third one, we will increase the power consumption to meet the quality of service requirement. Okay, finally, this figure shows the best case scenario where the power consumption level remains the same for both of the algorithm, for the preferred link first algorithm and the QoS. And on the other side, the figure demonstrates how the delay event is triggered when the flow delay exceeds the threshold value. It was approximately 75 in our case. And then the proposed algorithm identifies alternative path with low delay, as you can see here in the blue color. Okay, the final part in this video, I would like to show you how the algorithm works in practice. Let us see. Okay, I prepared my test pad using Ubuntu operating system. Just right now I have opened two terminals. In the first one I will run the models, and in the second one the data center network topology, in our case FAT3 topology. I will send real-time and non-real-time traffic until the real-time video streaming suffering from delay and starts lagging. We will see how the algorithm find an alternative path to keep it under the specific threshold. So right now we started the streaming. So after a few seconds we will see how the video start to lagging and how the algorithm find the alternative path. As you can see right now, the video it's stopped and lagging. And let's back to the event and let us see what we have. As you can see, the real-time flow suffering from delay, and the path suffering from delay is this is the path, and this is the source and destination, and the path found by the Dijkstra algorithm. This is the alternative path to keep the quality of service at acceptable level. So thank you very much.